talk to you today a little bit. I'm not going to start over though. That's okay. No, I am going to say Melissa DeLucchi again so that people can hear how to say it. Yeah, software engineer for LINCC Frameworks. We are building Rubin science software tools. And I want to talk today to just kind of demystify what we do in LINCC Frameworks, why we exist, what we're trying to do within the LSST community, as well as give a little deep dive in the LINCC Frameworks project that I'm contributing to. Give folks a chance to ask any questions you might have. I hope someone else is going to monitor the Slack channel or Zoom chat and let me know if there are any questions, because
I'll monitor questions for you. Yes.
Okay, thanks. So this is a really short talk, so I'm skipping a lot of the background and motivation that I think I can assume people in this audience already have, that LSST is going to have a lot of...
I'm so sorry, are you sharing your screen, Melissa? You are. Okay, great.
Yes. You see a big table of stuff?
Yes, thank you.
Okay, cool. Yeah, so LSST is going to have a lot of data, and that's going to bring some new challenges, and we're going to need new software approaches for those challenges. The LINCC Frameworks team kind of got its start at the Data to Software to Science workshop, and I think some people on this call were even at that workshop, where a handful of common technical challenges bubbled up around the various scientific pursuits that were identified. And these science areas, as the leftmost column, roughly map to science collaborations. And then some of the columns further right map to dedicated engineering efforts that we're taking on under the LINCC Frameworks umbrella. I'm going to be talking some today about our approach to cross-matching, which is that first column with a ton of check marks. So there's a lot of interest in this field. But we also have folks on the team working on photometric redshift with Rail and scaled time series analysis with tape. And maybe if this talk goes well, we can get invited back to dig into some of those other topics. Similar to the ISSC, we're not really motivated by individual science use cases or science goals, but kind of a net for the interesting technical challenges that lie outside the scope of any single science collaboration. So we want to enable science by developing good, scalable, productionized software and algorithms in collaboration with the broader community. I guess I skipped over this point. I'm not a scientist. I'm a software engineer. Yeah, that's not my thing. I like to make really awesome, fun software. So as a team, we are generally engineering focused and want to collaborate with other software efforts and make sure that we're minimizing the duplicated effort and contributing to standard community tools and libraries where possible, so that we are really getting the broadest scope that we can. We have a team filled with scientists and software engineers to make sure that we're targeting the most impactful changes we can. So the LINCC Frameworks project is a collaboration with a handful of institutions, CMU and University of Pittsburgh here in Pittsburgh, as well as University of Washington in Seattle, and the LSST Discovery Alliance and NOIRLab. Our PIs are Andy Connolly and Rachel Mendelbaum, who are in this picture over here and over here, and our engineering director, Jeremy, over here. And we are supported by the Schmidt Futures. So thank you, Eric Schmidt, for that. These are all the members of our team. We're split about 50-50 between software engineers and scientists, and we're split about 50-50 between Pittsburgh and Seattle. And even among the software engineers, we're split about 50-50 with people with like an astro or physics background, like an undergraduate degree, for example. So within our team, there's already a lot of cross-functional collaboration with a mix of different histories and experiences and skills and personalities. So we love collaborating and we want to do even more of it. This whole thing really is just one big advertisement, and here are some smaller advertisements inside. We have a Tech Talk series that runs the second Thursday of every month at 1 p.m. Eastern. We have a link here. I'll also send some links in a follow-up, because there's going to be a lot of stuff that I talk about here. These talks showcase the work done by kind of the broad software community within astronomy. Everything is recorded and put up on YouTube. So far, we've had talks from alert brokers, in-kind contributors. We've even had a couple of our own engineers lend talks to this series. In October, we're going to have a talk on Zooniverse and citizen science. November, we've got something around deep learning and machine vision. We'll figure that out. And in December, we will have some of our incubator talks to talk about the results of this incubator process. What is that? These are the LINC incubators, or LINCubators as we like to call them. This is a 3-month intensive collaboration between science teams and LINC Frameworks. The science teams, if selected, get collaboration with super cool software engineers, potentially some computing resources to get some results for your fun science questions, as well as some funding. So I guess thanks, Eric Schmidt, for that too. There's a lot more information at this link, as well as a full-length talk given on this topic and how the process works. But I can give a rough overview here. We are looking for folks who want to engage with LSST and LSST data, which luckily I think describes everybody on this call, which is pretty fun. We're looking for well-defined projects that someone could actually make tractable progress on in a 3-month period. Things that we can carry out now with precursor data or simulated data, since we don't really have the real data yet. And people who want to collaborate with us in a fun collaborative environment. And would benefit a broad range of folks in the astronomy community and the LSST community specifically. So we run 3 of these a year. Each one is about 3 months long. There's a 1 or 2 page proposal, short, informal. We're informal folks too, and as well as another informal follow-up conversation to help us get some more information about the folks that we would want to select. The first session is ongoing, just has another couple of weeks left. And then immediately after that, we're going to start our second session, and we have already selected the folks for that. The third session, the applications are currently open and will be open until October 16th. So get those applications in. Last plug I want to give is for the LINC Python project template. We've used this within our own internal projects as well as the incubator teams to codify our team's best practices for Python code organization, and can help get projects started with good documentation and integration tests, as well as GitHub automation, and lets the science teams really focus on the science. In addition to the best practices that we have codified within the template, we have a lot of other documentation for our opinions on best practices and extending the template for other things you might want to do at our Read the Docs site. Okay, so the deep dive that I promised a little while ago will be on HipScat and LSDB. HipScat being hierarchical progressive survey catalog and the large survey database. And these are pretty tightly coupled. We'll talk a little bit more about both. From the beginning, we're really focusing on the issue of efficient catalog cross-matching and trying to unblock multi-survey science. Scalable cross-matching was identified pretty early in the LINC Frameworks process as a pretty underfunded problem, and one that was impacting all kinds of science, from transients and variable stars to dark energy and cosmology. So these are both built from the beginning, targeting efficient catalog cross-matching. And HipScat is a proposed file structure for spatially partitioning the astronomical catalogs so that we can perform some cross-matching downstream. If we're going to go through the trouble of converting all of our catalogs into this new format, let's make it even cooler so that it could be potentially a new standard for bulk download and storage of survey catalogs. And LSDB is a Python library that we're building on top of HipScat for analytics. And if we're building something cool for efficient cross-matching, let's go ahead and make it be a general parallel processing engine that can suit a number of needs. I'm not going to say all of them, but hopefully a good amount of them. So digging a little bit deeper, we are coming up with a new way to store and access these large LSST-sized catalogs, taking a cue from geographic information systems where we partition our space dynamically so that we can have larger tiles or larger pixels in areas of lower information density and smaller pixels in areas of higher information density, so that there's about the same amount of data per pixel, even if it's not the same area in the sky. So for example, this is an all sky catalog where in the galactic pole, there's not a whole lot happening. That's kind of, dark. And then in the galactic plane, there's more information there, and we would see smaller pixel sizes. To do this, we're using hierarchical surveys. They're not quite progressive, but that's okay. We'll get there. And HEALPIX, which is the hierarchical equal area isolatitude pixelization. We are combining a bunch of existing concepts in a novel way, which I really like. HIPS is already a well-established directory structure for storing tiles of varying sizes. HEALPIX is an existing technology for producing tilings of equal area on the sky, and also have different orders, and so different sizes of tiles. And we can adaptively use different HEALPIX orders to get a sky partitioning with about the same number of objects per tile. We're also not creating any new file formats. It's really just a file structure that we're creating. We're using Parquet for the object storage, JSON and CSV for the basic metadata. Nothing new and shiny, all things that existing readers and technologies and libraries can interact with. So those files that I was talking about, this is an example of a HIPSCat catalog that would already be on disk for, in this case, Pan-STARRS detection table. We have a couple of Parquet files. These are the common metadata and metadata files that make it a Parquet data set that is readable by other libraries as well. Catalog info and provenance info have some interesting metadata about where these catalogs came from, where you might find specific fields, stuff that's kind of unique to being a HIPSCat. Partition info talks about the distribution of the tiles in space and where you can find areas of the sky within the Parquet files. And this is how our data looks on disk in these Parquet files. This is just the HIPS structure to specify the HEALPIX order, and then underneath that, the individual pixels that are at that order. I've talked a little bit about Parquet files, and that's what we're using. And this is kind of what it looks like inside Parquet files, though they are a binary format. It's kind of just like a binary CSV. They do some cute, clever things in storing columns individually and metadata separately. So they have a lot of chunks inside the file. They're able to compress the chunks individually so that if you have, say, something like flag fields or this other thing where it only takes on a couple of values, that can be compressed very effectively, as opposed to some of these other fields that you would want to use a different compression approach for. So what can we do with something once it is a proper HIPSCat catalog? Anything that can read Parquet files can then interact with a HIPSCat. So that includes Dask and Ray and Hive and Hadoop and whatever your favorite Parquet interaction software might be. It's also pretty tractable to subset large catalogs just to the data that you are interested in. So spatially subsetting it, given some region, a cone or a polygon, it's pretty easy to figure out which partitions are going to cover that region and query from only the files that are contained within that region. In addition, because Parquet is columnar and stores all of these columnar chunks, we have pretty efficient selection of specific columns. So if you only care about some columns in some portion of the sky, we can subset that data without having to look at all the data first. From this, we can get scalable analysis of a single HIPSCat using parallel per file analysis. These files are all going to be roughly the same size, so you can throw a bunch of workers at them and they'll just pick up the work as that's available. And they should take roughly the same amount of time to process through each file. So we can do complex searches to find populations that we're interested in through spatial or columnar comparison. We can also compute more rich features on top of our data, create new columns, do any kind of fun user added functions there as well. And then the thing that we're really excited about that we started with was the scalable analysis of a bunch of different HIPSCats together. So because we have them spatially partitioned, this enables spatial cross-matching of the data sets using LSDB, which is the large survey database. And this is an astronomy aware layer on top of HIPSCat. This is a Python analysis library built on Dask which some of you might be familiar with. You can think of it as kind of like parallelized pandas. There are a lot of the same pandas-like operations that you could take on, an individual CSV file, and then Dask will handle parallelizing those operations over many files. And catalog cross-matching really is the fundamental use case that we are thinking about. We're doing our cross-matching in a fun parallelized way. And so we also want to provide the rest of the parallelization to folks so that they can unlock doing robust parallel analysis on the full LSST dataset without having to write a lot of the parallelization yourself. Some sample workflows that we're working through now. We're working with some other time domain folks to do what we're calling the AGN MVP, which is a spatial crossmatch of SDSS and PanStars and ZTF, and just looking at objects that are in the milliquaz AGN catalog and joining those light curves together. So all of the detections for at least PanStars and ZTF, doing color correction, doing some time domain analysis stuff, running structure function over all of these AGNs and seeing what happens. We've already got a lot of the LSDB API and data ready to go, and the LINCC Frameworks tape team is working on color correction, light curve, smushing together stuff and structure function stuff. So we're very excited about that collaboration and what it could mean for other time domain work. But other kinds of workflows would be pretty much any full sky catalog population studies, full sky inference pipelines. We might be able to help with things like training and evaluation, but that's not likely to be where the biggest challenges are as we expand to LSST size data sets. Just about any data workflow that fits in kind of a MapReduce model over catalog data is probably going to work well within HipScat and LSDB. Because the data is partitioned into a bunch of smaller files, the operations can be pretty easily parallelized, and LSDB and Dask are going to handle the workers and reading the data so that you can just focus on the science of the data. So that's more or less what the things do, or we hope they're going to do. Our immediate plans for these things are working with archive partners like Fornax, which is a NASA collaboration with a handful of NASA archives, to test our format on a variety of catalogs while we're kind of targeting the LSST-sized data sets. Because we're also targeting crossmatch, we want to make sure that those other catalogs can be put into the HipScat format so that they can be crossmatched later. We're trying to incorporate IVOA standards into our metadata and API wherever possible so that this can be kind of a sustainable approach for many years to come, and drafting IVOA standards so that we could share all of this stuff with the world. And that's going to take a little while. On the LSDB side, we're working to get our cross-matching being really scalable and robust with Dask, and propagating that metadata that we do store within the HipScat all the way through the pipelines to make sure that you can use this metadata that you've worked so hard to get the little bits onto your columns. We're integrating with TAPE, which is the time series analysis and processing engine. It's another team at LINCC Frameworks working in the time domain, and really focusing on usability and maintainability so that this can be used for LSST size datasets and others. You can find more information on all of these things at this link, which I'll also send out later, or join the HipScat working group if IVOA standards are a thing that makes you happy and excited. We should talk more. Yeah, so that's all that I have prepared. Thank you.
Great, thank you so much, Melissa. I have to do my virtual clap. Okay. So we do have time for some questions and discussion. Okay, well, I see Ronaldo has already raised his hand, unless he's clapping. No, he has a question. Go ahead. I think you're muted, Ronaldo, but I don't know how. You are still muted. If you want to type your question, I
Hello?
can.
Hello, can you hear me?
Oh, yeah.
Hello? Yeah, it's working
Yes.
now? Okay.
Yes.
Okay. Okay, Melissa, that's a very nice talk. That's kind of a data engineering talk to me. So that's maybe my question is a very technical one, but concerning the LSDB, parallel processing solutions, how is going to using GPUs? And if it's the PyCUDA language will be applied, or okay.
I don't really have a good answer for that. I have not thought about any good GPU workflows. I don't know. That's a great question. Maybe we can follow up with you on that.
Yeah, just to jump in quickly, if you have use cases where GPU code is particularly useful, we are definitely looking for use cases. So please send them our way. We'd love to discuss them with you.
Yeah, in general, if folks have, any quick questions about this stuff, we're happy to talk about it. If you have like a 3-month long question that you might have about this, then the LINCcubators would be a pretty good avenue for that.
Great. Okay, so maybe follow up offline. Jeff, you have a question.
Yeah, thanks. For obvious reasons, I'm interested in more detail about tape, the time series analysis. Do you happen to have a quick summary of the different tools and things that are there, and just more information about what that is all about?
Yeah, I don't know if Kostya would like to also give a quick intro, but he's working on that as well. Really targeting scalable time domain stuff. So taking in 1 million or 1 billion light curves and doing some, function over all of them and getting the summary statistics out of that. Because that's a tough thing to do.
Right.
Could I follow up, Melissa? Yeah, so tape is more about infrastructure for such an analysis, not about analysis functions or analysis method themselves. So you could think about it as, pandas or a data frame library for time series, which is built to be flexible enough and useful for time series analysis with distributed parallelization with the desk. So it's kind of summary.
Yes, got it.
So even though we're not focusing on the individual algorithms that you might apply to time domain science, the kind of overall structure, though we have contributed some, for example, the multi-band Loam-Skarkle to AstroPy, which who knows, you might have some words about.
So in particular, are there, when you mention 1 million or 1 billion time series or whatever, that's kind of daunting. Do you have specific, requirements for the speed of algorithms that you can consider, and any formal thing like that?
No, I don't think so. If you want to take a long time figuring out your summary statistics, I think that's okay with us. This is more in terms of getting the right work to the right workers.
I see. And so you focus more on the sort of retrospective context as opposed to real-time alert, notice, and so on. Yeah.
Yes. Yeah.
Okay, great. So thanks.
Thanks.
Okay. Great. Can I ask a quick question, Melissa? For the oh no, I've already forgotten this. The catalog cross-matching software you guys are developing. Is there a plan to have that integrated into like LSST brokers or anything to access, to use this, but behind the scenes?
Potentially. Also potentially trying to understand HipScat and cross-match as a service so that the brokers could be using that for a faster cross-match as alerts come in.
Yeah, super cool. Okay, if there are no other questions, we can thank Melissa again. And Jeff, you can feel free to share your screen.
Okay, I'll try to do that. And see if
Uh,
it works.
Email.
Can you see full screen with cursor?
Yes, I can see that.
Okay,
So
great.
yeah, feel free.
Yeah. I'm sorry.
Feel free to go ahead.
Okay, thanks. Thanks for, I really appreciate the invitation to give this presentation. In the upper left is, I searched for the official logo you're supposed to use when you retire from NASA, and I couldn't find one, so I invented one that focuses on NASA's big new initiative into UFO studies, which is obviously the wave of the future. Sorry, that's a joke. So basically, the two things I'm trying to kind of sell here are, in essence, two specific time domain tools. One of which I think of as the Swiss Army knife in the frequency domain, and the other the same thing in the time domain. But you'll see what I mean by that that statement. So the basic issue that I guess, at least the way I look at it, is that this is from the official website, and I just wanted to highlight the fact that the basic issue is that there's going to be lots of really great time domain information, time domain science that can be done concerning variable sources, but the irregular sampling in time is an issue, and that's what I want to talk about, is dealing with that little detail. And here's a kind of a quick survey of the kinds of things that I thought of, but I think everybody on this call can probably add more science things. I don't know quite how to call these, but they're things you could look for in light curves of variable sources, obvious periodic, quasi-periodic signals, transients and flares, and also don't forget random processes, not just deterministic things like periodic signals. And classification is another thing that I'm sure people here are more familiar with than I am. But anyway, and just to quickly mention sampling in time, obviously we're not dealing with evenly spaced data with missing points or gaps or anything like that. The timing is basically random. And I guess the actual nature of the sampling, the sort of the underlying process is kind of unknown. Maybe I can be educated on that, but as near as I can tell, it's going to be, statistically speaking, it's a rather peculiar process with some random elements, some systematic elements, and some unknown elements. And please, if I'd welcome any comments either now or at the end on the nature of the underlying process. In statistics, there's a lot of literature where one assumes uneven sampling, but you know what the random process is that the sampling obeys, so to speak. And I think that's really rare in astronomy, but maybe the Rubin Observatory will be kind of different in that aspect. But anyway, a little classification stuff first, just to put things in context. There's kind of two different domains that people talk about, the frequency domain and the time domain. Of course, frequency domain you can also think of as a scale domain. Frequency and scale are just inverses of each other, and you can plot things as a function of frequency or as a function of time scale, 1 over frequency. But the time domain is time is a little different there. You're stretching things out in time, and there's sort of a mixed domain that people don't think about too much, but we'll see in a minute what what that really means. But there's another kind of aspect, and I struggled for terminology here, what to call this, but there's sort of a global kind of analysis where you essentially want to characterize the time observation interval as a whole. You want to get a light curve and analyze it, and somehow pops out some overall statistic that describes the behavior over the whole time interval t. But there's an alternative, a local analysis, where you're interested in specific structure at specific times within the time interval, like you're hunting for transients or flares or things like that. And again, there's a mixed domain. And I sometimes go overboard in constructing diagrams like this. I apologize, but for those of you who have never heard of morphological boxes, or Fritz Zwicky's really interesting idea for sort of helping with science questions in a way, and it's a simple thing where you have a two-dimensional array, or maybe higher, where the rows and columns are things, and at each intersection of the row and column index, so to speak, there's a possibility, some of which you may have already thought of and worked on, but it sort of forces you to think about things that you might not have otherwise thought about. That's just a quick analysis on the morphological astronomy that Zwicky wrote a whole book on, which is really interesting. Anyway, this just shows this classification scheme that I mentioned, that the domain that you're interested in are the rows, and the columns are the the columns are the domain, and the rows are the focus, or whatever you want to call the global versus local. And within each of these boxes, you see kind of standard things. Wavelets are interesting because they sort of are both global and local at the same time, and so on. Anyway, I don't want to get bogged down in this, but I think some of you may have not seen these ideas. So let's focus a bit on this global analysis, and just repeating, you dump in a light curve into your analysis scheme, and a statistic pops out that characterizes the time series as a whole. And obvious examples are just basic statistics, like the mean and variance and kurtosis and skewness and all that kind of stuff. But also things like the Fourier transform, power spectra, correlation functions, and so on. And I want to emphasize as I call it, the Swiss Army knife, is this algorithm, if you will, for calculating the complex Fourier transform for arbitrarily spaced data. This is the formula, and I guess the periodogram generated from this, the so-called Lohm-Scargill periodogram, is kind of well known, but it's not as well known, although it was in some of my original papers. You can calculate using essentially the same arithmetic and logic the full complex transform, which is exhibited here. And so you can generate not just the power spectrum, but the phase spectrum, the complex phase, or the argument of the complex transform, is known as the phase spectrum, which has some scientific interest too. A few comments on this, on the use of this periodogram. Don't use it on evenly spaced data, and that seems like a pretty obvious thing, but you'd be surprised at how often people use it on evenly spaced data. It's not horribly bad in the sense that you can get the same answer as you would get with the FFT if the algorithm is working right. But the case of evenly spaced data is a bit singular in the computation. So unless your algorithm unless your implementation is really careful about that, it can go wrong for the singular case of evenly spaced data. Don't use it. That may be a strange comment, but often the periodogram is used for no particular reason. And in particular, there's a notion that somehow it corrects for the sampling in the data. It does not. It simply allows for the uneven sampling of the data. To correct for or undo or deconvolve the sampling, you have to deconvolve a window function, which can be done, especially using the Fourier transform, but with some caveats about zero denominators and noise amplification and so on. And then there are these well-known issues about the frequency array to use for the periodogram or things derived from it. The fundamental is pretty well defined, but the Nyquist frequency for uneven spacing is ill-defined. The nominal thing to do is to just use multiples of the fundamental out to, I guess there really should be a factor of a half here, because typically the Nyquist frequency is a half what I've written here. But anyway, one of the neat things about the algorithm is you can calculate it for an arbitrary frequency array. If, for example, if you're interested in a logarithmic frequency array, you just put those numbers into the algorithm, and it can be any frequency array that you cook up. It could have a big gap. You could have a low frequency interval and a high frequency interval, and it's trivial to calculate it. So why do I call it the Swiss Army knife? Well, there's lots of things you can derive from the Fourier transform. The periodogram or the power spectrum is well known, but the autocorrelation function is just the Fourier transform of the power, which can be implemented with a fast Fourier transform. If you're interested, you can even invert the Fourier transform and recover the original data, at least approximately. I'll give an example. But you can also calculate, if you have two time series and you're interested in correlations and cross quantities like the cross correlation function or the cross spectrum, those are easily derived from this initial Fourier transform. So it's a Swiss Army knife in that it has a lot of different things sticking out, tools that you can use once you have the complex Fourier transform itself. Here's an example of the calculating the autocorrelation function from some actual data. The data aren't too important, but comparison here is between the approach I mentioned before, that you calculate the periodogram and then calculate the Fourier transform of it to get the autocorrelation. But you can also interpolate the data, and you see there's a difference. There are some issues with a possible bias in either one of these approaches that I think are interesting unsolved data analysis questions. Here's a thing about inverting the raw data, and this is, if you think about it, the raw data can be considered as a set of delta functions at specific times. And so when you do the inversion, if you include a high enough frequency interval, you can essentially recover these delta functions, including the zero between them. Well, this seems kind of silly, but by introducing filters and various things, you can do smoothing or interpolation with this approach. But this is just, I think of this as more of a check on the fact that the algorithm is working right, and that you can recover a bunch of delta function samples with the inverse Fourier transform. All right, let's go to the time domain. Again, you have a input of a time series, but now what you're interested in is structural details as a function of time, and this is an example of that, namely a segmentation of the time series into intervals using the so-called Bayesian block algorithm. And this is, like I said, it's local analysis where you're looking at structure in the time domain. Examples of things that you might be looking for are things, flares, or other kinds of transient events, mode switches between different modes in the source, shot noise events. And I'll just quickly, I apologize for people on this call who have heard me talk about Bayesian blocks before, but here's a quick summary of it. And basically you need to define a model for the shape of the block, typically a constant, the piecewise constant thing I showed earlier on some data is an example of that. And you need a objective function or cost function or fitness function, whatever you want to call it, for how well the data are described by whatever the model is, and a likelihood. The standard thing to use in the applications is the likelihood for a constant model across the block. And you need this additivity condition that the total cost of the model is the sum of the cost of the blocks, but that's, especially in the likelihood context, that's pretty natural. And the magic of the Bayesian block algorithm is here highlighted in red, namely, you're considering, you want to partition the data in the best one of all possible partitions, but the number of possible partitions is exponentially big for any reasonable time series. 2 to the n is impossibly big, but the magic of dynamic programming allows you to determine it's an exact solution for the optimal partition in time of order n squared, or under some conditions of order n. And the number of blocks is automatically determined by the algorithm, which is, here's another example of the yellow histogram is just it's an arbitrary evenly spaced histogram, just so you have something to look at of some photon data. And by the way, the reference to sort of the underlying idea behind the Bayesian block algorithm and dynamic programming is this old paper by Richard Bellman. And anyway, I think it's pretty obvious what's going on here. And I usually give kind of a long spiel about how great the algorithm is. And one of the great things about it is the input data can be in any mode you want. Of interest here is the standard just sampling at arbitrary times. But there's also a real-time mode of the algorithm which might be of some interest, namely, if you add one new data point, rather than go back and recalculate the entire optimal partition, it's an easy incremental step to add a new data point. So there's kind of a natural real-time aspect to the algorithm, which might be useful in big data applications. And here's the kind of one new idea, and this is pretty speculative. Is it possible that Rubin observatory data might be used to detect unresolved gravitational lensed AGNs, or Einstein rings? And here's the idea, that the standard model for the light curve of a simple gravitational lens source with two images is this, that you get one image and then another image is the delayed version of the same variability with some caveats about microlensing and so on. But that can be, there's a magnification factor and a delay factor built into the optics, the gravitational, strong gravitational lensing optics. And if you just do some algebra, you can show that the autocorrelation function, R here is the autocorrelation, for this model is the sum of three terms, sort of the standard autocorrelation with its peak at zero lag, but then there's two terms. And so one of the basic approaches that has been used in the literature is to simply look for a peak in the autocorrelation at other than zero lag to kind of try to detect this delayed signal, but that's not ideal. But anyway, there's some work on a better approach where you solve for both the magnification factor and the delay simultaneously. And the idea is very simple. You solve the above equation for the unlensed light curve as a function of the observed light curve and the two parameters. There are various ways of doing that, and I'm working on some new ideas there. But then if you define a metric for the solution, and it can't be just how well it fits the data, because this is an exact solution. So this metric can't be just the residuals and the model fit. It has to be something else. And that's where the art is in figuring out what a good metric is. But then you find the lag and the magnification factor simultaneously by optimizing this this metric. So I think this is probably a pretty long shot because of the sparsity of the data in time compared to the thousands of data points that for other examples. And also this by definition is going to be for faint unresolved sources, and it seems like it could be a test to see if it's a lens system or not. But anyway, just tossing that out as a question, and I think I'll stop there. So glad to take questions. So.
Great, thank you so much, Jeff. I'll also do. Okay, so I'll open the floor for any questions. Sorry, my internet's very unstable. For any questions. And if not, I'll ask what is the half-baked and naive question about this last point. So we know that these lags, are redshift are wavelength dependent, and I'm wondering if it's possible, how distinct are the lags due to lensing versus just lags that we expect naturally as a function of wavelength in AGN disks?
Yeah, the lags for gravitational lensing are not wavelengths dependent. It's chromatic. So whereas other lags might be wavelengths dependent, and that could be a way to distinguish other in that context, other variability could mimicking this is kind of the noise or the corrupting signals that you want to discriminate against. But yeah, that's a good point.
Okay. Question, yeah, go ahead.
Yeah, thank you so much for the talk. You haven't mentioned, if I missed it, the fast implementation of Lomscarville when you used FFT to speed up the calculation. Could it be also used for this Fourier transform to reconstruct both amplitude and phase? And what are your recommendations of when we should and when we shouldn't use fast Lomscarville? Thank you.
Oh, okay. Yeah, that's a good point. There is a fast version of the periodogram. I forget George Ribicki, and I'm drawing a blank on the other author, and other people have developed it too, where you sort of use a trick. It's an approximation, but it's a very excellent approximation and I haven't looked into it. I assume that it would be completely straightforward to make a fast version of the full complex transform. And so that would make it much faster. As it stands, it's an n squared algorithm, but it could be made n log n in that way. And I think the other part of your question was, when should you do it? Well, maybe I was too harsh when I said don't use it. If you have our data that's not evenly spaced, it's the best thing you can do to get into the frequency domain. I guess my only point is you shouldn't think that you have corrected for the sampling. And if conditions are right, you can correct for the sampling. You can deconvolve the window function. It can amplify the noise in your data. And you have to worry about whether if the denominator can be 0 in some conditions, but typically that's not too big of a risk, because unless the sampling has some built-in quasi-periodicity or something like that. So no, it can be useful if you're interested in looking for trying to detect periodicities or quasi-periodicities, and as a step to these other correlation functions and so on. It's I think it could be generally used in, but you should keep in mind other approaches to, for example, period finding. There's maybe a dozen or so different approaches to that. Some based on folding of the data at an assumed period and scanning over the assumed period, and things like that. So even though I'm sort of promoting it as a Swiss Army knife, there are other tools in the toolbox that one might use. So I hope that answers your question.
Thank you so much.
Great. Eric, go ahead. We have a few minutes left.
Yes, thank you very much. Hi, Jeff. Thank you for a fascinating presentation. I have a comment and I guess a built-in concern, not about the methodology, but about the use of the methodology for the LSST, the Rubin Observatory LSST Wide, Fast, Deep Survey. So this is 80 or 90% of what Rubin's going to be doing for the next 10 years. I think my comment is that I think Bayesian blocks is going to be very useful for asking when does something change, because roughly speaking, you read the website, it's going to observe the sky every 3 nights. But in fact, it's going to switch between 6 bands, and you're not going to know the colors of things. So really, it's really every 16 nights, 18 nights, that's 6 times 3. And so you actually get a very sparse and not quite regular data set with only a few points until you have a year or 5 years or 10 years of data, when you actually get hundreds of points. And so people are going to be dealing with very sparse data for many, many months at the beginning of the survey. So I think the Bayesian blocks can ask the question for billion objects, has it changed? And that's very useful, because there's many reasons for it to change. A star can change, an AGN can change or something, but just to have a Bayesian block for that is nice. But what worries me is that people, including the LSST built-in functionalities that Eric Belm has written about, are going to be running Lom-Scargill periodograms on these sparse data sets. And the problem is that when you have irregular spacings and sparse data, tens of points or something like that, and you run any sort of a Lom-Scargill, is that you get all these peaks all the time, which are not physically real. And
Yes.
and I'm worried that the community is going to that really Eric Bellman, the LSST functionality should not give the Lom-Scargill peaks when they are unreliable. And it's not that hard to do that through simulation, and to show that unreliable peaks are going to be quite common in the first few years. So do you have any comments? Bayesian blocks will be reliable for sparse data. Lom-Scargill periodograms will often be unreliable for sparse data. That's my comment.
Yeah. Yes, I do. Great comment. Ironically, the reason I was a few minutes late zooming in, I was on a Zoom with a Fermi presentation of some work that did exactly what you're talking about. It took some sparse data and did a periodogram, and people forget that this power spectrum is an inherently noisy estimator. And anyway, you have to be careful. It's not like you can't do anything with it, but yeah, you're absolutely right. On the other issue, at the very beginning, you hinted at something, and I'm trying to remember, somebody actually worked on an approach that transcends the algorithm that you're using, where you try to sort of use a model for the spectrum of the source so that you can tie together the data at different bands, at least in a simple way, so that you don't have to wait until you come back to exactly the same band, that you can get some information. And I
Yes,
forget
there-
who was working on that. Maybe it was you, or maybe it was.
No, it was my colleague, Jonsuk Tak, who has an ARMA, an autoregressive model for irregular spacing with 6 bands. Very interesting paper from 2020 that LSST people should look at. And because autoregressive phenomena are not uncommon. And there's maybe 1 or 2 others that try to do the multi-band problem with very sparse data. It's not simple statistically. Tak
Right.
is a statistician, he got it right.
But you can do better than having to wait for the same band to be repeated, I think.
Yes.
And,
Thank you very much, Jeff.
sure. And just a footnote, I agree with your sort of implicit view that Bayesian blocks is really statistically, it's the ideal way to detect changes in a light curve. It's built in. If you have a data stream and if it's constant, the algorithm in its real-time mode tells you when it first departs from being constant.
Yes.
Thanks.
Great. Okay, this brings us to the hour. Thank you so much, Jeff, and thanks again to Melissa for 2 really great, engaging talks. And be on the lookout for the next announcement in about a month for our next talk in this series. Great. Thanks, everyone.
Thank you very
Thank
much. Bye-bye.